66 million years ago, the extinction of non-avian dinosaurs shattered the existing ecological hierarchy, leaving the planet open for a new wave of mammalian dominance. Freed from the constraints of their former reptilian overlords, mammals underwent a rapid, aggressive expansion in both diversity and physical scale. For millions of years, the evolutionary ceiling for land-based mammals climbed steadily, culminating in the Eocene epoch with the rise of Paraceratherium. This giant, hornless rhinoceros was long accepted by the scientific community as the undisputed heavyweight of the mammalian world, a benchmark of biological mass that seemed insurmountable. However, the history of natural scale is rarely static. A chance discovery in 19th-century India unearthed the remains of an ancient elephant that defied these established metrics. Known as Paleoloxodon Namadicus, this colossus forced a rigorous re-evaluation of the maximum size mammals could achieve. By challenging the long-standing supremacy of the Paraceratherium, the Namadicus shifted the focus of paleontological inquiry from simple categorization to the mechanics of extreme gigantism. This discovery serves as a critical turning point, demonstrating that our understanding of prehistoric life is inherently tethered to the limits of the fossil record and the ongoing evolution of comparative analysis. The evolutionary trajectory of the Paleoloxodon genus represents one of the most consistent and aggressive pushes toward biological gigantism in the Cenozoic era. While the genus is often associated with the later, massive forms found in Eurasia, its foundational story is rooted in the African landscape. The earliest universally recognized member of this lineage, Paleoloxodon recki, emerged during the early Pleistocene, roughly 1.8 million years ago. Even at this stage, the genus had already established a template for extreme physical dominance. Male specimens of P. recki reached shoulder heights comparable to the total height of a modern giraffe, with body masses often exceeding 12 tons. Recent 2024 re-evaluations of 7 distinct specimens have pushed these estimates further, suggesting a range between 4.5 and 15.3 tons. This scale effectively cemented P. recki as the dominant elephantid within its African range, leveraging massive size and specialized dental morphology to command the available resources. Approximately 800,000 years ago, environmental pressures, specifically increased aridification and shifting grassland habitats, triggered a significant migration event. Populations of P. recki moved out of Africa and into the broader Eurasian corridor. This geographic expansion was a catalyst for intense evolutionary divergence. Once established in Eurasia, the lineage branched into several distinct paths. One primary outcome was the emergence of Paleoloxodon antiquus, a massive species that frequently exceeded 15 tons and stood taller than nearly all known theropod dinosaurs. However, the genus also demonstrated remarkable evolutionary plasticity. As these elephants migrated into isolated island environments across Europe, such as Crete and Cyprus, they followed a drastically different trajectory: insular dwarfism. Over generations, descendants of these giants shrank to adapt to restricted island resources, eventually resulting in some of the smallest elephant species to ever exist, with some individuals measuring smaller than modern pigs. This stark contrast between the continental giants, the massive P. antiquus and the eventual P. namadicus, and their diminutive island counterparts highlights the genus's extreme adaptability. By the time the lineage reached its peak in the form of P. namadicus, it had transitioned from a localized African ancestor into a diverse, continent-spanning group that redefined the upper limits of mammalian body mass through a relentless, multi-million-year commitment to scale. The historical unearthing of Paleoloxodon namadicus remains began in the 1830s, when researchers affiliated with the British East India Company recovered fossilized material from the central regions of India. These initial findings, primarily consisting of a skull and various postcranial elements discovered near the Godavari River, immediately signaled the existence of a prehistoric elephant of unprecedented proportions. However, the scientific community faced significant classification hurdles during this period. For over a century, experts debated whether these remains belonged to the same genus as modern African elephants, Loxodonta, or represented a distinct, ancient lineage. It was not until 1942 that the creature was formally and definitively assigned to the genus Paleoloxodon, resolving the taxonomic ambiguity that had shadowed the discovery for decades. While the formal classification process was protracted, the physical evidence of the animal scale was impossible to ignore. Early paleontologists identified a femur that was markedly larger than the corresponding bone of a triceratops, a comparison that immediately established the specimen as a heavyweight contender in the prehistoric record. Based on this single femur, researchers estimated a shoulder height of approximately 4.35 meters, or 14.3 feet, concluding that the individual was significantly heavier than any recorded African elephant. This initial assessment provided a baseline for the species' massive stature, yet it was only the beginning of the realization regarding its true dimensions. The magnitude of the discovery became clearer following the recovery of a second, even more robust femur. This specimen was measured at roughly 20% larger than the previous find, providing empirical evidence that Palaeoloxodon Namadicus occupied a weight class fundamentally different from other known terrestrial mammals. This discovery served as the primary catalyst for re-evaluating the upper limits of mammalian size. By highlighting the existence of a creature that dwarfed modern elephants and rivaled the largest dinosaurs, these early 19th century finds forced a shift in paleontological perspective. The sheer scale indicated by these fragmented remains suggested that the species was not merely a large elephant, but a biological anomaly that challenged established thresholds for land-dwelling mammals. These early, hard-nosed measurements established the foundational consensus that P. Namadicus was a colossus, setting the stage for subsequent, more precise volumetric analyses that would eventually solidify its status as a record-breaking giant in the natural world. The 2015 study remains the high-water mark for these estimates, suggesting a prime Palaeoloxodon Namadicus stood 5.2 meters tall at the shoulder. At this height, its back was level with the heads of most giraffes and towered over every terrestrial predator in history, including the Spinosaurus and Tyrannosaurus rex. The study's volumetric analysis calculated a maximum weight of 22 tons. This mass did more than just outclass other mammals, it allowed the elephant to rival famous sauropod dinosaurs like Diplodocus and Brontosaurus. For the first time, the rhino-like Paraceratherium had a legitimate challenger for the title of the largest land mammal to ever walk the earth. However, a hard-nosed assessment requires acknowledging the limitations of the data. The primary issue is the fragmented nature of the fossil remains. Because paleontologists are working with incomplete skeletons, these massive figures rely on scaling up isolated bones, which introduces significant statistical uncertainty. Even the lead author of the 2015 study explicitly stated that the 22-ton estimate should be taken with a grain of salt. This skepticism is a necessary safeguard. When dealing with the upper limits of biology, small measurement errors in a femur can lead to ton-size discrepancies in the final weight estimate. More recent research has attempted to stabilize these numbers. A 2023 study re-evaluated the evidence and placed P. Namadicus at a slightly more conservative 19 tons. Crucially, the same researchers applied their methodology to Paraceratherium, concluding it weighed approximately 17 tons. This suggests that while the rhino might have held a slight advantage in height, the elephant was the denser, heavier machine. This downward trend for the rhino was further supported by a 2022 paper that analyzed several Paraceratherium specimens and found an even lower weight range between 11 and 12.4 tons. Even at the 19-ton mark, the scale of P. Namadicus remains unprecedented. This weight is 3 times that of a modern African bush elephant and roughly 300 times the mass of an average human. It comfortably exceeds the weight of any known theropod dinosaur. Regardless of whether the peak was 19 or 22 tons, the implication is clear: the mammalian body plan reached a level of structural dominance that was previously thought impossible for anything without a dinosaur's respiratory system. This massive frame required more than just size, it required a specialized mechanical design to keep the colossus functional. The massive frame of Palaeoloxodon Namadicus required a specialized mechanical architecture to remain functional. At the center of this design was a dense, exceptionally sturdy skull. This species featured a prominent parieto-occipital crest, a massive ridge of bone running across the top of the skull. This was a critical attachment point for the splenius muscles. These thick muscle groups provided the necessary leverage to support a head that carried immense weight. Without this reinforced anchor, the animal would have lacked the neck strength to move its skull or, more importantly, to wield its primary tools. Those tools were its tusks, which reached lengths of up to 5 meters, or 20 feet. These were straight or slightly curved ivory spears, mirroring the morphology of its relative, P. antiquus. Each tusk could weigh more than a large predator, yet the specialized skull and muscle configuration allowed the animal to use them with precision. In a practical sense, these were versatile instruments of both offense and defense. They were capable of piercing rivals or clearing obstacles, turning the animal's sheer mass into a focused, lethal force. This mechanical power was fueled by a relentless grazing lifestyle. Isotope ratios and teeth morphology confirm that P. Namadicus primarily targeted C4 grasses in open environments. Sustaining a 19 to 22 ton body required a staggering 150,000 calories every single day. To meet this quota, the animal likely spent the vast majority of its waking hours feeding. This creates a clear evolutionary trade-off. While its size made it nearly invincible, its caloric dependency forced it into a state of constant vulnerability. By spending nearly 16 hours a day with its head down in open grasslands, the species was tethered to specific habitats. The sheer time required to eat left no margin for error. Any environmental shift that reduced grass density turned this giant's greatest asset, its size, into a logistical liability. This dependency meant that despite its physical dominance, the animal's survival was precarious, dictated by the stability of the very corridors it traveled. For a creature of such immense proportions, the primary threat was never a traditional predator. Its sheer mass, thick hide, and massive tusks rendered it effectively immune to the apex carnivores of the Pleistocene, including Smilodon, hyenas, and the colossal crocodilian Ramphosuchus. An adult Palaeoloxodon Namadicus was simply too large to be considered prey. However, this biological invulnerability met a new variable with the arrival of modern humans. While the species coexisted with early hominids for approximately 30,000 years, the relationship likely shifted from passive avoidance to active conflict. Evidence for this interaction remains indirect, drawn from related species like P. antiquus and P. recki, which show clear signs of butchery and hunting by early humans. These findings demonstrate that our ancestors were already highly proficient at targeting megafauna, likely employing projectile weapons to bypass the elephant's defensive bulk. While the sheer size of a fully grown P. Namadicus might have deterred direct assault, its intelligence and complex herd behavior suggest it was a social animal that prioritized the protection of juveniles. Humans likely exploited these social dynamics, potentially using coordinated tactics to isolate younger or weaker individuals. The eventual extinction of P. namadicus, occurring between 50,000 and 25,000 years ago, was likely the result of a compounding crisis. A significant cooling trend during the late Pleistocene fundamentally altered the landscape, shrinking the open grasslands the species relied upon for its 150,000 calorie daily intake. As the habitat fragmented, the animal's caloric dependency became a fatal bottleneck. This environmental stress likely coincided with increased human pressure. The timing of the elephant's population decline correlates suspiciously well with the advancement of human hunting technology. While climate change reduced the carrying capacity of the environment, the introduction of sophisticated projectile weapons provided the final push, turning a once dominant megafauna into a vulnerable target. By the time the climate stabilized, the massive energy requirements of the Namadicus could no longer be met by the changing, less productive landscape, leading to the collapse of its population. The extinction was not a single event, but a convergence of ecological instability and the arrival of a new, highly adaptable predator that could effectively bypass the animal's natural defenses. Palaeoloxodon Namadicus stands as a testament to the extremes of mammalian evolution, officially reclaiming the title of the largest land mammal known to science. Its vast geographic expansion across Asia, from India to Japan, underscores a remarkable ability to dominate diverse landscapes. While classification debates persist regarding its regional variants, its legacy remains tethered to the persistent quest for scientific accuracy. Today, we view this giant through the lens of its closest living relatives, the African bush and forest elephants. As our analytical tools improve, we continue to uncover the hidden chapters of Earth's biological history. Our world is beautifully diverse, keep exploring.